Guys, now we discuss mathematical induction. Let us see what is mathematical induction, where we use it, and how do we prove or how do we solve the problems based on mathematical induction. So before starting this, you should know what is well ordering principle. So it says that every non-empty subset of Z plus contains a least element. To understand this principle better, let's look at an example. Consider the set of positive integer. Consider the set of positive integer 1, 2, 3, 4, etc. This set is well ordered because it has a smallest element. It has a smallest element 1. Every other element in the set is greater than 1, so 1 is the least element. If you see here, every other element in this set 2 is greater than 1. Next is all other elements are greater than 1, means 1 is the least element. Suppose I start with the number 2, 3, 4, 5, 6. This is also well ordered, means 2 is the least element. Every element in this is greater than 2. This is the least element in the set. You may think, why I am talking about only Z plus. Suppose you consider the real number set R. Real number set, it has from minus infinity to minus 1, 0, plus 1, 2, etc. infinity. So does this set has the least element? No, because least element it starts with minus infinity, so we don't consider that number for the calculation purpose here as a least element. Therefore this number set, real number set, has no least element. So that's why we don't consider this here. So we consider only Z plus or natural numbers. Natural number set. So every non-empty subset of Z plus is set of positive integer contain the least element. Only this set has the least element. Or we can say that the positive integer set Z plus is well ordered. Is well ordered. Well ordered. Now induction principle. So induction principle, it says that suppose we take a statement S of n is an open statement which involves the positive integer n. It is a mathematical statement. Suppose we need to prove that this statement is true for all n greater than or equal to 1, means all positive integers. N greater than or equal to 1 means Z plus positive integers. Then how do we prove? First we consider S of 1 is true. Okay, so first we take n is equal to 1 and we see that whether S of n is true. Second is we assume this statement is true for n is equal to k. Assume it is true for n is equal to k. So if it is true for some n is equal to k which belongs to Z plus, then S of k plus 1 is true. Okay, so assume that n is equal to k is true, prove that S of k plus 1 is true. Then conclusion part is S of n is true for all n belongs to Z plus. This is induction principle. Mathematical induction. Suppose we wish to prove some statement S of n is true for all integers n greater than or equal to 1, then we consider the method of mathematical induction. So it says that first step we call it as basis step. In basic step, we verify the statement S of 1 is true. S of 1 is true. If it is true, then we consider the induction step. How do you prove this? You take the statement S of n and put n is equal to 1 and see that the LHS and RHS will be equal to will be same. Then we say that basis step is true, or S of n is true for n equal to 1. Next is induction step. So in induction step, assume S of n is true for some n is equal to k, where k is greater than or equal to 1, or k is a positive integer. Then show that S of k plus 1 is true. How do you show this? You have to start with n is equal to k, use some mathematical principles or mathematical formulas, then show that S of k plus 1 is also true. So if it is true, then we conclude that by mathematical induction, S of n is true for all n greater than or equal to 1. This is the principle of mathematical induction. So in short, first we have to assume that S of n is true. S of n is true, S of n we have to consider, then we have to verify that it is true for n is equal to 1. If it is true, then assume that it is true for n is equal to k, and prove that it is true for n is equal to k plus 1 also. If this is happens, then conclusion part is by mathematical induction S of n is true for all n greater than or equal to 1. Now let us take one example. Let us consider S of n is the given statement. Here the question is, prove that for each n belongs to z plus 1 square, 2 square, 3 square, etc. n square. So sum of these numbers, first n numbers, is given by 1 by 6 into n plus 1 into 2n plus 1. So this is the given equation that we need to validate for all n belongs to z plus. That we need to prove the LHS is equal to RHS by using mathematical induction, and it is true for all positive integers. Okay, for that let us take S of n is the given statement. So 1 square, 2 square, 3 square, so on n square. This is equal to 1 by 6 into n into plus 1. Right, now let us take the basis step. What do we do here? We have to verify whether the statement is true for n is equal to 1. For n is equal to 1, S of 1 is the statement. So here n square we have here, therefore I will take only that term in the above equation, and RHS part is 1 by 6, n is 1, so 1 into 1 plus 1 into 2n, 2 into 1 plus 1. So 1 square is 1 is equal to 1 by 6, so 2 into 3 divided by 6. So this is 2 into 3 is 6. So we get 1 is equal to 6 by 6, this cancels, so 1 is equal to 1. It means LHS and RHS both are same. Therefore, what do we conclude? Therefore, S of n is true for n is equal to 1. So basis step is verified. Next, induction step. Induction step. Here what do? We assume S of n is true for n is equal to k, where k is greater than or equal to 1, it is a positive integer. Then using this we find that using this means S of n is S of k, we are replacing n by k, so 1 square plus 2 square plus 3 square etc. K square is equal to k. What is that equation? Here we have n, so we have to replace this by k. So 1 by 6 into k plus 1 into 2k plus 1. Now next step is very important. It is, here we have k square, isn't it? 1 square plus 2 square etc. k square. What is the next term of this series? What is the next term of this series? Yes, k plus 1 whole square. So add that term on both sides. Add k plus 1 whole square. This is next term of the series. Next term of the series is k plus 1 whole square on both sides. So we get this 1 square, 2 square, 3 square, so on, plus k square plus k plus 1 whole square, k plus 1 whole square is equal to 1 by 6 into k plus 1, 2k plus 1 plus k plus 1 whole square. So you have to add k plus 1 whole square on both sides, right? Now what do? You have to simplify the RHS part. How do you simplify? 1 by you can take k plus 1 whole square, k plus 1 common. You take k plus 1 common, then what remains here? K into 2k plus 1 by 6 plus k plus 1. Okay, then k plus 1 into, so here you can cross multiply or just multiply the numerator, we get 2k square plus k plus 6k plus 6 by 6. Next step, equal to k plus 1 into 1 by 6 I can write here, 1 by 6 is a common, then k plus 2, 2k plus 3, 2k plus 3. So this is the simplified form. Now this is equal to S of k plus 1. How do I write this is equal to S of k plus 1? Now check here. What is our S of k? Let me take here. What is our S of k we have taken? S of k is RHS part. RHS part is 1 by 6 into k plus 1, 2k plus 1. Okay. What is S of k plus 1? If you replace k by k plus 1, what do we get? 1 by 6 into k plus 1 into k plus 2 into 2 into k plus 1 is 2k plus 2. So we get 2k plus 3. This is S of k plus 1. This is what we got here. This is what we got here. That's why we are labeling it as S of k plus 1. See, the verification part is easy. What answer you have to get at the end, you can expect. How do you expect? First you see, how do you expect is, suppose S of k is this, replace just k by k plus 1 and this is the equation you get. So after simplification of this part, at the end you have to get this equation. at the end you have to get this equation, so that will be equal to s of k plus 1. Right. Now we write what is the conclusion. So we assume that s of k is true, and we prove that s of k plus 1 is true. Therefore we write the statement, thus the statement s of k plus 1 is true whenever the statement s of k is true for n greater than or equal to k greater than or equal to 1. Therefore, by mathematical induction, this statement is true for all n greater than 1. Therefore, s of n is true for all integers n greater than or equal to 1 by, so is true. So you can write here itself, by mathematical induction s of n is true. S of n is true for all n greater than or equal to 1. This is the proof. Similarly, you can try the second example. Is I tell you how to solve this, you can try yourself. So prove that by mathematical induction 1 plus 2 plus 1 plus 2 plus 3 plus 4 plus etc. plus n is equal to 1 by 2 into n plus 1. So how do you prove? Follow the same procedure. First you take this as s of n. Okay, take this as s of n, write the statement as s of n. Okay, then basis step, verify this is true for n is equal to 1. So here you have 1, no? So s of 1 will be n is equal to 1 by 2 into n plus 1. So if you s of n is this, so 1, if you s of 1 will be 1 is equal to 1 into 2 by 2, this cancels. So 1 is equal to 1, basis step is true. So s of 1 is true. S of 1 is true. Next to induction step. Induction step, you have to assume that it is true for s is equal to k. So you can write is assume it is true for n is equal to k. N is equal to k. Then s of k you take, write the equation. Then which term you have to add here? What is the next term of this? Obviously k plus 1 means here k, so k plus 1, add k plus 1 on both sides, and simplify the RHS part. You will get simplify RHS, you will end up with s of k plus 1. Then write the conclusion as we done in the last example. Similarly, you can solve this also. Third example, suppose we have the equation 1 square plus 3 square plus 5 square plus some 7 square plus so on plus 2n minus 1 whole square. This is the equation given to prove 1 by 3 n into 2n minus 1 into 2n plus 1. Prove by mathematical induction is true for all n greater than or equal to 1. This is the question. So induction step you have to take. So S of n is the given statement. You write the given statement as S of n. S of n is the given statement. You write the equation as we done in the first example. Then basis step S of 1. S of 1 is 2 minus 1 whole square is equal to 1 by 3 into 1 into 2 minus 1 is 1. So this will be 3. So 2 minus 1 is 1. 1 is equal to 1. So basis step is true. Next to induction step. Induction step, assume what is that, n is S of n is true or n is equal to k greater than or equal to 1. Now write S of k, write the equation S of k. Then look at the term. Here 2n minus 1 whole square is the last term of the series, which is the next term of this series. So that next term of the series is, after writing this, add. So next term of the series is given by 2k plus 1 whole square. So you have to add 2k plus 1 whole square on both sides. After adding, simplify RHS. If you simplify RHS, you have to end up with S of k plus 1. S of k plus 1. So what is the expected answer you have to get? What is the expected answer you have to get here? That is, assume this is S of k, then S of k plus 1 will be 1 by 3 into k plus 1 into, okay, then here 2k plus 1, 2k plus 1, so 2k minus 1 cancels, we get only 2k, and here if you replace n by k plus 1, so what we get, 2 into 2k plus 2 plus 1, so 2k plus 3. Okay, so this answer, this is nothing but S of k plus 1. So this answer you have to get at the end. So here you have to get this answer. That equation you have to get at the end. Then write the conclusion. Okay, so in this way we prove the equations by using mathematical statements by using mathematical induction, and it is very much useful in validating the algorithms in computer science. Suppose some algorithm is there, you need to check whether it is true for all numbers, then we can use mathematical induction.